Okay, so for our first example, we're gonna try to evaluate here the root of 9 minus x squared over x squared dx, right? Okay, so again, as always, try to figure out, can I do a substitution here? And really, unless we have an x outside of the root here, then there's no kind of substitution that can be a regular straightforward substitution. So we're gonna need a trig substitution, right? So we're gonna need x equals to 3 sine theta, right? Because it's of this type here. All right, now, when we do, a regular u substitution, we also need to sub dx. So that comes to the differential here, right? Dx is equal to 3 cosine theta d theta, right? So that's another component for our trig substitution here, right? And let me just draw the triangle here for reference. Sine of theta is going to be equal to x over 3, all right? Which means our triangle here looks like this, right? This is theta. Hypotenuse 3 is x, here the opposite, and then our adjacent is going to be root of 9 minus x squared. Okay, so now we're ready here to substitute. So my new integral in theta, right? Once I make my substitution, there are no more x, right? X needs to be substituted away in some form, right? And the way that's done here, so 9 minus x squared becomes root of 9 minus 9 sine squared theta. All right, and my denominator is x, so that becomes 9 sine squared theta. And then d theta becomes 3 cosine theta d theta. Okay, now right now it looks a bit of a mess, right? So let's start kind of simplifying things. All right, so I'm going to factor out the root 9, right, since it's inside the root. So that root 9 becomes 3 square root of 1 minus sine squared theta times 3 cosine theta d theta, and then all of that over 9 sine squared theta. Okay, and now what we'll see is we have a factor of 9 in the numerator, a factor of 9 in the denominator, so that's going to simplify to 1. All right, so continuing on here, we get, okay, the root, right? My coefficient is 1, and inside the root, I get 1 minus 1 minus sine squared theta. Now I apply the formula, the identity, which is cosine squared. Root of cosine squared is just cosine. All right, so here we get cosine, and then we get another cosine here. So we're going to get cosine squared theta over sine squared theta d theta. Okay, so we do get a lot of things to reduce here. And now the goal is, how do I integrate something like this, right? So if it was a product of cosine squared, sine squared, then I can kind of figure it out that way. But now that it's not, I'm actually going to take a different approach. Cosine squared over sine squared is cotangent squared of theta, d theta. Okay, all right. Now from here, I'm going to use an identity, right? Because again, cotangent squared, that integral is not a straightforward integral. But if I use the correct identity, I do get a couple of straightforward integrals, right? So if this is true, then that means that cosecant squared theta minus 1 is equal to cotangent squared. And this actually does simplify this significantly, right? All right, because I do know the integral of the cosecant squared, right? That is a straightforward integral. It is the cotangent, excuse me. All right, so this equals to cotangent theta minus theta plus c. All right, and excuse me, I'm missing a negative there, right? Because the derivative of the cotangent is a negative cosecant squared theta. All right, but I'm not quite done yet, right? My initial integral asks for me to solve a dx type integral. So here's where I need to go back to my triangle and figure out what are these values in terms of x. All right, so the cotangent, so tangent is opposite over adjacent. So cotangent is adjacent over opposite. So we get, don't forget that negative of 9 minus x squared, right, the adjacent, right, over the opposite, which is x. Now here, what to do about theta? Well, that's where this comes in. Right, here, let me scoot up here. If my initial substitution was something like this, well, this is true if and only if theta is equal to sine inverse of x over 3. And here is where that angle restriction comes into play. That angle does fall between negative pi over 2 and pi over 2. And we'll assume that it does. So now we get minus sine inverse x over 3. And as always, don't forget the plus c. All right. And there we go. Now we are able to evaluate an integral, which at first would look really complicated. Right? And now we're able to do that with the appropriate trig substitution. All right, now here's another thing we can do with our new kind of trig substitution technique is, let's say I wanted to find the area of an ellipse. All right, so let's say I have an ellipse, just a general ellipse, right? A plus B, right? Where we'll call this part A, this part B. And I want to find the area of this whole ellipse, right? Now I'm going to use symmetry to my advantage here. So symmetry, I'm going to find the area here. So the area of the whole ellipse would be 4 times that integral right here. All right. So now in order to find that integral here, I need to have some function in terms of y. Right, so I want to find my dA, right? But in order for me to find that first, I need to find a function. This is not a function yet. It's a relation, but here, I just need to do some algebra here. I'll solve for y, so we get y squared over b squared. Excuse me, this is a squared over b squared is equal to 1 minus x squared over a squared multiplied by b squared. We get b squared 1 minus x squared over a squared. Taking the root, now usually when we take the root of a square, it'd be plus or minus, right? But I'm just going to take the plus one because that's the top part of this curve here, right? The minus one would be down here. So y would be root of b squared is b, square root of 1 minus x squared over a squared. Okay, now I want it to look like my substitution forms, so I'm going to have to do a little factoring here. So I'm going to factor out a 1 over a squared. 1 over a squared, which means here the resulting form is a squared minus x squared. All right, again, if you distribute, right, if you're factoring out a 1 over a squared, then when I multiply it through, it's going to be a squared minus x squared. All right, and notice that if you do distribute, here, you get back your original expression, which is what we want, right? I don't want to change it. Just do a little bit of factoring here. Okay. All right, and then taking the root here, 1 over a squared is 1 over a outside the root. Okay. All right, so all that to set up the integral for the area to be 4 times the integral from 0 to a, right? I integrate along the x of b over a, square root of a squared minus x squared, dx. All right. And now it becomes a one of our trig substitutions, right? So we're going to let our substitution here be let x equal to a sine of theta, which means that dx is a cosine theta d theta. All right, and then our triangle, we have sine of theta is equal to x over a. So we got theta, hypotenuse is a x, and then the adjacent is a squared minus x squared, right, from the Pythagorean formula. All right, so now let's do our sum. So I'm going to take out the b over a since it's just a constant. So we get 4b over a. The integral, oh, actually, getting ahead of myself here. These limits only apply to, excuse me, only apply to x. So 0, when x is 0, right, sine of theta is equal to 0, which means theta is 0. So that doesn't change. So that's when x is 0. When x is a, we get sine of theta is equal to 1. And due to our angle restriction, theta is pi over 2, right? That falls within the range of pi over 2 and negative pi over 2. So that becomes our new limits of integration. Okay. All right, so now plugging in here, square root of a squared minus a squared sine squared theta, and then our dx was a cosine theta d theta. Okay, and then factoring out here on a squared here and taking the root of that is a, but there's another factor of a here. 0 pi over 2. Actually, let me just write this out here. So we get a 1 minus sine squared theta times cosine theta d theta, right? And again, factor out an a squared, took the root of that, which is a times the a here. So we get a squared root of 1 minus sine squared theta. All right, and then continuing on here. Here, I'm going to again factor out that a squared. One of the factors reduces with this a here, so we get 4ab from 0 to pi over 2. Inside the root is cosine squared. Take the root of that as cosine times another cosine. We get cosine squared theta d theta. Okay, and now it comes down to solving this integral. All right, it is a square of cosine, so let's use the power reducing, the double angle formula. So that tells me we have 4ab, the integral from 0 to pi over 2 of 1/2 1 plus cosine 2 theta d theta. All right. All right, factoring out I'll bring the half outside the integral. So that becomes 2ab. And I have inside the integral 0 to pi over 2 of 1 plus cosine of 2 theta d theta. All right, and this is two straightforward integrals, right? So we have 2ab, and then the integral of 1 is theta. Here, the integral of cosine is a positive sign. Now, I do have to account for that 2 theta, right? So essentially the factor of 2, which I don't see out here, so I need to divide it out. All right, so the whole thing, sine of 2 theta divided by 2, okay? Because again, right, what you want is when you take the derivative of this, you want to get back to cosine 2 theta. So by chain rule, derivative of sine is cosine 2 theta. Derivative of 2 theta is 2, so it will reduce with that factor there. No need for the plus c since it's a definite integral. All right, so when I plug in pi over 2, I get pi over 2 here. And then the rest is 0, right? When I plug in pi over 2 for theta, we get sine of pi, that's 0. And the lower limit, when I plug in 0, we get 0. Sine of 0, also 0. So really it's just pi over 2. And then when I multiply it by my 2ab, we get pi ab as our area for that whole ellipse, right? And this makes sense if you think of, it's an intuitive result if we think of the area of a circle of radius r. That's pi r squared, Right? And if you think of AB, those are like the major and the minor axes. You can think of them as two different radius for my ellipse, right? Where this is for this particular drawing, the major radii and then the minor radius. Okay, so it's the result here. If we were to kind of guess at it from the beginning, we would probably guess along those lines, right? The radius had to show up in some way.